Hi, and welcome back. My last video, once again, prompted some good questions in the comments. And to be fair, my last video did contain a seeming contradiction. On the one hand, I described the phase shift from minimum phase EQ as natural and wholesome, while the pre-ringing from linear phase EQ is diabolical and evil. But on the other hand, I advocated linear phase filters for crossover duties, despite the pre-ringing, and despite the fact that we apparently can't hear the phase shift from minimum phase crossovers. Why is that? Part of the problem might be the fact that I exaggerated slightly for comic effect. The work of the devil was meant to highlight how unnatural pre-ringing is compared with the very natural and normal phase shift from minimum phase filters. But it probably also overstates the problem. I've never actually been bothered by pre-ringing issues with normal real-world EQ settings. In fact, when I had to create audible pre-ringing for a tutorial video, I had to work quite hard for it. You need really steep, extreme filtering at very low frequencies, plus a source signal which contains a combination of low sub-bass and a hard transient. So basically just a kick drum. In practice, my objection to linear phase EQ is much more about being reluctant to put up with the latency issues and spend the extra CPU cycles for no audible benefit. But I'll come back to linear phase filtering shortly. Let's start by talking about phase shift. Here's FabFilter Pro MB running just a single band, requiring one single crossover, which is of course two filters, a low pass to isolate content below the crossover, and a high pass to isolate content above it. I haven't adjusted any gain settings or dialed in any dynamics processing, so we're just seeing a flat frequency response. If I switch plugin doctor to show phase instead, we still see just a flat line. That's because we're in dynamic phase mode, which doesn't actually put any crossover filters in the signal path at all. At least, not unless I solo or mute bands. Dynamic phase mode is actually, strictly speaking, dynamic EQ. If I change the gain for this band, we introduce a shelving filter set to produce the correct gain difference, and we see some shelf EQ type phase shift appear on the graph. Dynamic phase mode, therefore, means no phase shift when the frequency response is flat, but dynamic, constantly changing phase shift when the band is compressed or expanded. But the phase shift always remains quite gentle, as you'd expect from a shelving EQ. If I switch to linear phase mode, obviously the phase shift disappears. It doesn't matter what I do with the gain, phase remains flat. But if I switch back to show frequency response, that definitely changes when I change the gain, so it is working as advertised. Okay, now let's try minimum phase. It looks just the same on the frequency response, but the phase shift is now really significant around the crossover frequency. I showed this phase plot without much explanation last time, which was perhaps remiss of me, so let's break it down. This slightly confusing vertical line at the crossover frequency isn't a sudden discontinuity, and it doesn't mean the phase suddenly plunges down through zero at that point. In fact, it indicates the frequency at which we get 180 degrees of phase shift and turn the waveform fully upside down. As phase is measured on a circle, shifting the phase by more than 180 degrees starts to bring you back round the other side of the circle. So this vertical line is the point where the phase shift has maxed out, disappears off the top of the graph, and reappears at the bottom. Two things to notice about this phase shift. First of all, it's static and doesn't change at all when I change the band gains. This is a good thing, as static phase shift tends to be less audible than dynamic, changing phase shift. But on the other hand, it's way more extreme than the phase shift introduced by dynamic phase mode. If I used dynamic phase mode in a parallel configuration, the phase shift would be largely irrelevant, just as using shelf or bell filters in parallel is generally fine with no serious side effects. But if I ran the minimum phase crossover in parallel, that 180-degree phase shift at the crossover would result in total cancellation of those frequencies and a notch filter. But I hear you say, what if you're not running it in parallel? Why is the phase shift a problem in that case? And here I am, toggling bypass on a minimum phase crossover that's processing my voice. Can you hear the difference? I know I can't, But perhaps absolute phase is something that only some people can hear, rather like the way only some people have perfect pitch. So if you can hear a difference with the crossover switched in, let me know in the comments, preferably with a description of how you perceive that difference, as this could be very interesting. For now, though, I'm going to assume your ears and brain are configured the same way as mine, and the phase shift from this crossover is totally inaudible. And now, let's try running it on just the left channel. You're hearing that now, right? Okay, so there's 3 possible scenarios here. You might be watching this on your phone in mono. I won't judge you if so. I also watch a lot of YouTube like that. In that case, the left and right channels are being summed, creating a notch filter at the crossover. So you're hearing a significant change in frequency response, not the phase shift directly. Second possible scenario. You're listening on stereo speakers, so the left and right channels are mixing together acoustically before you hear them. Again, you'll be hearing some sort of notch filter, less perfect than with mono playback, but nevertheless a significant change in frequency response. Final scenario. You might be listening binaurally on headphones or earbuds. In that case, these 2 signals only mix together inside your brain. If you can hear a difference with the crossover switched in, that means you can hear static phase shift, right? I'm going to suggest that if you're not already using headphones or earbuds, pause the video now and plug some in. Okay, you all set for the binaural test? Now again, I can't necessarily assume that you're all perceiving this the same way I do. So again, let me know in the comments if you can hear the difference. I definitely can. It's not subtle. What's more, I can tell the difference when the phase shift swaps to the other ear. That tells me that we can hear phase shift, but most of the time we don't care about it. Or perhaps we can't hear absolute phase, but we can hear phase differences. A bit like having relative pitch instead of perfect pitch. So my philosophy is, if I don't fully understand what conditions are required for phase shift to become audible, I can't say with certainty that the phase shift from a minimum phase crossover will never be audible. And we need to remember that we're talking about a large amount of phase shift, a full 180-degree phase reversal for every set of crossover filters. And if you're running 5 bands of compression, that means 4 sets of crossover filters. With 24 dB per octave minimum phase crossovers, that gives us this overall phase plot. If you were trying to make phase shift audible, something like this might be a pretty good starting point. Okay, now for a null test. Nulling the minimum phase crossover with the dry signal predictably reveals huge differences around the crossover frequency. We've actually created a perfect bandpass filter here, literally the opposite of the perfect notch that results from adding the wet and dry signals without the polarity flip. So let's switch to linear phase and see how much pre-ringing we see in the null. None at all. That's interesting. My analyzer is set to show down to minus 100 dB, as usual. I've decided, slightly arbitrarily, that if differences are smaller than that, I simply don't care about them. So the linear phase filters meet the strict definition of the term transparent much better than the minimum phase filters, in the sense that when there's no processing going on, the signal is totally unchanged. The crossovers themselves don't alter the signal in any way at all, not even with an arguably inaudible phase shift. Until you dial in some compression or change the relative band gains, nothing is happening whatsoever. Now, I stand by my argument that if artifacts are too low in level to show up with these analyzer settings, they're too small to worry about. But nevertheless, let's try reducing the floor even further, just to see how low in level those pre-ringing artifacts are. Well, that's as low as it goes. Still nothing. What if we try different frequencies? Nada. Steeper crossover setting? Still nothing. What if I boost the noise level? Well, finally, with the noise signal at full scale, we just about start to see the differences peep up above minus 180 dB on the analyzer. And at those levels, I'm tempted to write them off as floating point errors. I'm certainly not going to worry about them. So what's going on here? We know that all filters ring, and that linear phase filters ring equally before and after the impulse. But where is that ringing? I'm going to try to answer that question with a different demonstration. Here's an impulse. More specifically, it's a Dirac spike, which simply means one full-scale sample with the rest at 0. I'm going to process it through an instance of ProMB with a single crossover, which I've set as steep as it will go, just to make any ringing as extreme as possible and easier to spot. And I'll solo the low band, so we're only testing the low-pass filter. Let's render that. Then I'm going to mute the low band instead of soloing it and test just the high-pass filter. Let's render that as well. And let's take a look at the results. If I zoom in vertically, it's easy to see the pre-ringing in both files. But a few things I need to point out. First of all, notice how short the pre-ringing is. Just a couple of dozen samples, even with a pretty steep 48 dB per octave filter. Also notice it's symmetrical around the impulse. This is what makes it linear phase, apparently. Don't ask me for the mathematical explanation why. Clever people tell me this is so, and I believe them. But final thing to note, and the most important in this context, if you haven't already spotted it, look at the folder track above, with both waveforms superimposed on one another. The ringing for each filter perfectly mirrors that of the other. The high-pass filter is equal and opposite to the low-pass filter, so their ringing is equal and opposite. And when the bands are recombined, as I can simulate by rendering this folder track, they simply cancel each other out. How awesome is that? This suggests that the linear phase crossover is actually 100% perfectly transparent when you're not processing the signal. It's not just so good that you'll never hear the artifacts. There are literally no artifacts. It's exactly the original signal. Which is quite remarkable, really. Now, of course, I don't suppose anyone loads up a multiband compressor only to leave it flat with no processing. So what happens when we start to compress the bands or change the gain settings? Well, of course, then the ringing will start to reappear. But unless you mute or solo bands, as I did for the impulse test, you're never going to get the full amount of ringing. In fact, the ringing will be proportional to the gain difference between adjacent bands, a bit like the phase shift in dynamic phase mode, and will probably always be cancelling out to a significant degree. So those are the rigorous tests. Now, for my subjective opinion, I have, on occasion, thought I could hear negative consequences from minimum phase crossover filters. I am, of course, human and just as susceptible to cognitive bias as anyone else, and also not immune to user error. Nevertheless, I've never had that impression when switching in linear phase crossovers. They've always sounded completely transparent to me. That's not hard evidence, of course, but it's another reason for me to personally choose linear phase crossovers most of the time. Except, of course, when I don't use crossovers at all. Dynamic phase mode can be really useful in ProMB. This mode might only exist because I badgered the FabFilter developers into making it. Let's talk for a moment about the implications of a dynamic phase response. There may be some debate about how audible a phase shift like this one is. Personally, I can't hear a difference when bypassing this all-pass filter in Volcano 3. But if I modulate that all-pass filter, I'm hearing that now. So a dynamic phase shift that's moving around or changing intensity is probably a bigger issue than a static phase shift that's not changing at all. This might be part of the reason why I have a preference for linear phase mode in Pro MB when I'm using very fast compression settings. But often I need much gentler and more sedate settings just to rein in a specific band of frequencies when they're in danger of getting out of control. In that case, dynamic phase mode sounds just as good to me as linear phase mode when compressing, and literally is exactly as transparent as linear phase mode when it's not doing anything and all bands are flat. But it does it without the latency and with a noticeably lower CPU hit. Alright, but wait. There's a related issue that I've also been getting questions about. What about linear phase oversampling filters versus minimum phase? Is the pre-ringing from those ultra-steep up and down sampling filters an issue? After all, we're not mixing that signal with any equal and opposite filters that will magically cancel out the artifacts, as in the case of the crossover. Let's find out. I'll start by testing the impulse that I used earlier, using Saturn II, which usefully provides a choice between minimum phase, low latency oversampling and linear phase, higher latency oversampling. I'll go with minimum phase first and pick the highest oversampling setting, although I don't think this actually makes much difference, and render it. And that looks quite alarming, actually. Look at all that ringing after the impulse. Now, having been assured by clever people that this is so, I'm expecting that when I repeat this test using the linear phase option instead, we'll see symmetrical ringing both before and after the impulse. And this is indeed the case. What has yet to be explained to me, however, is why the ringing is also much less extreme. It's lower in level and seems shorter as well, even allowing for the fact that half of it has shifted to before the impulse. If you're one of those clever people and you feel like explaining this, I'll be very grateful and will probably pin your comment. Anyway, let's try a null test. And just to show that FabFilter are not the only developers that know how to do oversampling properly, here's the drop from Cytomic. The mix knob is set all dry, so there's no filtering going on, other than the up and down sampling filters for the default 2x oversampling. And we're not seeing any difference on the analyzer. The Cytomic plugins allow you to switch oversampling modes independently for the up and down sampling stages. This is a feature that I find more interesting than useful, if I'm honest. But let's try switching the upsampling filters to minimum phase. And there's a big difference, clearly audible at normal monitor gain settings. If I downsample with minimum phase as well, the difference gets even bigger. Intermediate phase is, presumably, a halfway house with a smaller amount of pre-ringing combined with a smaller amount of phase shift. The difference is reduced, but still pretty big and still clearly audible. But back in linear phase mode, the difference drops below my don't care threshold. Let's delve down into the depths of the dynamic range again to see where in fact those differences are. And we do eventually see some in the minus 160 dB range. That's a kind of interesting pattern of differences, but still utterly insignificant in any real-world scenario. Let's set the low range back to a more sensible minus 100 dB. And note there is a way to reveal much greater differences. The upper frequency range for the analyzer is set to 20 kHz. But of course, with a 48K sample rate, we can theoretically go up to 24 kHz. And sure enough, there's a big difference. This doesn't really count, however, as we're seeing the intentional band limiting of the anti-aliasing filters. Those filters have to remove everything above Nyquist at half the sample rate, and as steep as they are, they nevertheless have to start rolling off below Nyquist to achieve that. I don't know if my ears ever cared about content above 20 kHz, but they certainly don't now, and I'm happy not to worry about stuff that high. And I'm going to speculate that much of the ringing of the oversampling filters is, whether naturally or through clever filter design, up in that region above 20 kHz, which is why it seems so startlingly low in level when we exclude that region from the analyzer. So there we have it. Pre-ringing may be the work of the devil, but I have sympathy for the devil when it comes to crossovers and oversampling filters. Even when I don't fully understand why, my tests tell me that linear phase is way more transparent than minimum phase, and my ears also agree. That's all for now. Thanks for watching.